Of electronegativities that gets inserted into the packet with the writing Lewis formulas on the outside. So anybody need the one here from Tuesday? Okay. Well, I think we finished the hour. Let's just do a quick check here where we were at the end of the hour. We were writing out some exceptions to the octet rules. We looked at less than an octet, more than an octet, and an odd number of electrons. Anybody have any questions on these three that we did at the end of the hour on Tuesday? All right, then today we are going to look at starting with a model of the carbonate ion. So we'll jump over here and we're going to write the Lewis structure for carbonate. And we'll start by writing out the formula for the carbonate ion, which is CO
3 negative,
charges 2 negative, right? So now if we were to determine the number of valence electrons with this one, we start with carbon, which has how many? 4. I know you were just joking. 4. Then we have oxygen. Each one here has 6. And how many oxygens do we have? 3. And the 2 negative charge means we have 2 extra electrons. So we sum these together. We have 18 plus 4, which is 22, plus 2 more makes 24. Actually, I don't want to do carbonate, but I think we're going to get the same number. Because I think Donovan was reading my mind and knew that I was intending to do the nitrate ion. Sorry about that. So we have 5, because I think we did carbonate here the other day, and I want to do something different. So in the end, though, we do the math, we're still going to wind up with the same one. It's just that it's a single negative charge, and this one here is 5 valence electrons, so these have the same total number. And they're going to be very similar in structure anyhow, but I want to look at this one again just to be different. So if we write out the Lewis diagram for this one, we'll start with which atom in the center. And surrounding the nitrogen atom, we would have 3 oxygens, looking something like this. Of course, this uses up how many valence electrons? 6 of them. That leaves us with 18. So then when we go ahead and assign those extra valence electrons, we then assign them as pairs to the surrounding atom. So we put in 2, 4, 6, 8, 10, 12, 14, 16, 18. Of course, now we've used up all of the valence electrons. We have 0 remaining. First, what's wrong with this yet? Nitrogen does not have the outer level filled. So what do we need to do here?
shift some electrons.
Shift some electrons. So now the question is, do we shift one here? Or do we shift this one down here? Which one do we pick to shift? Well, here's what happens. If you find yourself in a position of having to choose, if you put yourself in the position of having to choose, we have a phenomenon that is referred to as resonance. Resonance. Not always, but we usually have a phenomenon that we refer to as resonance. And resonance is described on your handout here like this. You say it is a delocalized bonding, which is a type of bonding in which a bonding pair of electrons is spread over a number of atoms rather than localized between 2 atoms. And we generate what's called a resonance description, which describes the electron structure of a molecule by having delocalized electron bonding by writing all of the possible electron dot formulas. So now, in plain English, what that means is this. I'm going to go ahead and take this structure that I just drew. I am going to copy this structure No, I don't want to do that. I want to undo that. Copy. I must have a way to do that better. Let's try this. Highlight it. There we go. We want to copy this. And now we want to paste it like this. And again, right here. And I'm going to repeat this structure 3 different times. Now what I'm going to do with it is this. In one of these, I'm going to show that we had taken this pair of electrons and assigned the double bond here. In this one, I'm going to take this pair of electrons and show we assigned the double bond here. And this last one here, I'm going to show that we've taken this pair of electrons and assign a double bond right here. Now, of course, if we were to look at just one individual structure of all these, what is this, just ignoring the rest of these right now, what are we still missing from this Lewis diagram? We're missing the charge. What else are we missing? Brackets, exactly. So we put in the square brackets on here and the charge. Square brackets in here and the charge. Square brackets around here and the charge. And then we're going to write in these arrows here to show that these electrons now are mobile. Now, what we don't want to think of it as this. There actually is not a double bond that's present in the nitrate ion. We write it as if there's a double bond, but they aren't. We say that these electrons that are present in here are delocalized. Now, if we think of what the term delocalized means, we have to first think of what the term localized means. If you have something like localized flooding, what does localized flooding imply?
Specific to a specific area.
Small scale.
Small area, exactly. It's limited to a single area. If you delocalize it, then you are spreading it out. Okay? So, delocalized bonding is what's happening here in resonance. This pair of electrons is not localized to this position. This pair of electrons is mobile and actually moves throughout the structure. Now, part of why that is significant, and part of why it's getting these props together here, is this. First of all, now these aren't nitrogen and oxygen atoms bonded together. What I am showing, though, however, is carbon atoms bonded together. In fact, if we start comparing distances going from a single bond between 2 carbons to a double bond between 2 carbons to a triple bond between 2 carbons, something happens to the bond length. In fact, if I put these in here, can you tell which of these is the shorter bond? The triple bond is shorter. And if I put this in here, this is maybe a little harder to tell, but you should still be able to tell which one is shorter here. The double bond is a little bit shorter here. So the longest bond between 2 atoms is going to be a single bond, then the next is going to be a double bond followed by a triple bond. Okay, so we talk about these in terms of being bond lengths. And bond lengths is something that's described on the back side of your handout here. It talks a bit about bond lengths and bond order. And it talks about the distance between the nuclei. The distance between the nuclei in a bond is referred to as the bond length. An approximate bond length for an atom joined by single bonds may be calculated by summing together the covalent radii of the 2 atoms involved in the bond. So when we were talking about those atomic radii the other day, those atomic radii then is, if you were to measure the distance from the nucleus of one to the nucleus of the other, you wind up finding what that bond length is going to be. Then we also define something called the bond order. And the bond order refers to the number of pairs of electrons in a bond as the bond order. And we say that the bond order depends on the bond length. And how does it depend? Well, here's how we first of all describe the order. If there's a single bond between 2 atoms, we call that a first order, or the bond order is 1. This one, the bond order is 2, and the bond order in this one is 3. So it's named after first, second, or single, double, and triple bond. So the bond order is 1, 2, and 3. So as the bond order increases, what happens to the bond length? It decreases. So again, as the bond order increases, the bond length decreases. And if we read this last statement here, it says, as the bond order increases, the bond strength also increases, and the nuclei are pulled closer together. So with a larger bond order, and we can imagine that if there's 3 bonds holding this together, it's going to be pretty rock solid, exactly. It's going to be more difficult to get them apart. So the bond strength is much larger with a larger bond order. But again, the bond length is going to be shorter. Now, how is that relevant? First of all, any questions on that? Okay, so then the question is, how is that relevant to what we just drew? Well, let's say that we ignored these other 2 structures. Let's just look at this one right here. Now, scientists have come up with a way, using techniques what are called spectroscopy, of measuring the bond lengths. And if we were to look at something like the nitrate ion, if we could look at each of these bond lengths, if we were to compare these 2 to this one, these 2 bond lengths would be longer than this one here. Okay, but that's not what we find. We don't find 2 long bonds and 1 short one. What we actually find is if we were to measure the bond lengths, the bond length appears as if it's about equivalent to 1 1/3 bonds. It appears as if they're all the same bond length, but instead of it being as long as a single bond, they aren't as long as a single bond, and they're not as short as a double bond. It appears as if they are about 1 1/3 bond lengths in terms of their distance. So the way we describe that then is that what must be happening then is that this pair of electrons is not confined to being shared between these 2 atoms. Instead, this pair of electrons basically distributes itself throughout the polyatomic ion in this case, and we say that its bond, or its location, is delocalized. So again, it spreads itself out. So what you can imagine then is that there's basically a single bond between all of them. That is a single pair of electrons between each one. A single pair here, a single pair here, and a single pair here. And then there's a 4th pair that spreads itself out amongst all of them. And that's what this attempts to show. This is what we call a resonance description. This is what is called a resonance description. And the whole set of them is called a complete set of resonance structures. These represent resonance structures. And again, you don't want to think of this as being a double bond that moves from here to here to here. That's not what's happening. It's not a double bond that moves, but rather it's a single pair of electrons that winds up basically distributing itself around the entire structure. Now, sometimes the way we represent it is like this. We might draw it, I guess, starting something like this, with the nitrogen in the center, surrounded by the oxygens, and we don't really worry about showing all of the valence electrons in here, but rather we show the delocalized electrons looking something like this. And then we would show the charge on that polyatomic ion. This is what we often refer to it as being a resonance hybrid. And so a resonance hybrid is really a hybrid of the resonance structures, where these dots here, or the dashed lines, are representing the delocalized electrons. So again, the delocalized electrons are represented by the dashes that go through there. And so now, when it comes to your homework, and of course our exam, which we're going to be doing next week, you do want to know the difference between a resonance description of resonance structures and a resonance hybrid. The resonance structures or the resonance description looks something like this. And the resonance hybrid actually shows that pair of electrons being distributed throughout that particular structure. Okay, so any questions on this particular one? So now, if we were to go to something like nitric acid, which is just a variation here on the nitrate ion. Let's say that we would want to write a resonance description for HNO3 showing resonance structures. Then also show the resonance hybrid. Hybrid. That's HYBRID. Okay, so now this is one that we would deal with a oxy acid. If we were to write out the formula for nitric acid, the formula is HNO3. We always start by writing out a single Lewis structure. So for the single Lewis structure, we need to first calculate the valence electrons. Hydrogen has 1. Nitrogen has 5. And oxygen has 6. And we have how many oxygens? 3 of them. So altogether we need 24. So then, when we write out the structure, which element are we going to put in the center?
Nitrogen.
Nitrogen. And the nitrogen we will surround with oxygens. And where is the hydrogen going to go? We should be able to pick out any oxygen. It doesn't really matter which one we pick out of here. So now at this point we've used up how many valence electrons? 8. So we have 16 left to go. Then what we're going to do is we're going to put in the remaining pairs of remaining electrons as pairs, the surrounding atoms. So we put in 2, 4, 6, 8, 10, 12, 14, 16. Well, now you see we're going to run into the same problem as we had before. And that same problem is now nitrogen still has to have a octet. So now we find ourselves saying, are we going to choose this one or are we going to choose this one here? So when you find yourself in a position of choosing, once again, then resonance is usually possible. But in this case, instead of choosing from 3 different ones, we're simply choosing from 2 different ones. So how many resonance structures do you think this one is going to have? Just 2. So we can take the same structure that we just drew out, and if you have copy and paste, you can do this. Ha ha ha, sorry you don't. All right. And we'll put it over here. And then, that's just because if I draw one beautiful the first time, then I can just copy it the second. That's not always beautiful the first time, right? So now, if we want to put this in, then what I'm going to do is, on the first one, get rid of a pair of electrons and put it in here, like this. And then on the next one, get rid of a pair of electrons, put it in like this here. And what else does this one need?
Charger.
This one doesn't need charges. Why doesn't this one need charges? It's neutral, yeah. What else does it need though? Yeah, it needs that arrow. Now remember what this arrow is not showing? This arrow is not showing that's flipping back and forth between these 2 structures. That means that the double bond doesn't go from here and then to here. What it means though is that we have a pair of electrons that is delocalized. And so if we were then from here, this is, by the way, now is our complete resonance structure. So that completes the first sentence. If we want to look at the resonance structure, the atom we put in the center is nitrogen. We'll put the oxygen here, 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 and here. And then if we want to show the delocalized electrons, where are we going to put it in? Just right here is the only place that it's going to go in. And so what this is telling us then is that the pair of electrons basically is delocalized and shared between these three atoms. That's what that resonance hybrid represents. Okay, so if we were to have a pair of delocalized electrons distributed amongst three atoms, then you have to show it being shared amongst three, and we show three different resonance structures. If there's only two possible resonance structures, then we put in the double arrow, and we're only going to show that lone pair, or that electron pair. It's actually not a lone pair, it's a bonding pair that is shared between those three atoms. So any questions that you have on writing out resonance structures? Donovan?
You use your pairs on that last oxygen with the hydrogen when you break the hybrid?
On this one here?
Right.
No, we don't need to. Typically in the resonance hybrid, we're really just trying to depict where those delocalized electrons are located. That's the emphasis in writing that resonance hybrid, is showing these electrons. The rest then are not as relevant. Okay. Anybody else? All right. Then the last piece that we're going to look at today. I think we've gone through most of these here. Sometimes we need to pick different structures, and I'm trying to find, here it is, a concept called formal charge. And formal charge now, if we were to talk about this, formal charge is not a real charge, it is a hypothetical charge. So again, it's hypothetical. It's something that isn't real. It's not something that, if you look at an atom, so you can say, oh, because it has this type of charge, it's going to attract. It has nothing to do with that. It's what we say is a hypothetical charge that we get that assumes that bonding electrons are shared equally between bonded atoms, and that lone pairs of electrons belong entirely to one atom. And one of the reasons why we use formal charge is that sometimes when we generate structures, we don't know why we observe the best structure the way we do. So we invent things like a formal charge to help us describe what it is we're observing, and then use it as a predictive tool to develop the correct structure for something else. So we'll talk about these rules here in just a bit, but we're going to generate some structures here which we apply rules of formal charges. And we're going to start with something like the sulfate ion. The sulfate ion. Now I think we drew this one out the other day. If we go back and look at the sulfate ion, we maybe drew that one out here. Let's see if we can find it. Looking right here, if we follow these rules. So if we want, we can go ahead and just take this one that we developed the other day. And of course, we put the sulfur in the center. And we surround it by these oxygen atoms. And then we put in the lone pairs around the oxygens. And then to make this technically correct, what we do is we put the square brackets around this here and here and assign a charge of 2 minus. Now what we're going to do here next is this. We are going to write a Lewis formula, write a Lewis structure that optimizes the formal charge on each atom. We're going to write a Lewis structure that optimizes the formal charge on each atom. Now, as far as what this means when we optimize formal charges is this. First of all, the way that we calculate the formal charge, we calculate it according to this definition. It says that the bonding electrons are shared equally between the bonded atoms, and the lone pairs belong entirely to one atom. So what that means, if we want to calculate that formal charge, is we take the valence electrons that are present on a free atom of that element, we subtract from it the lone pair electrons, and then 1/2 of the bonding electrons. And we subtract 1/2 of the bonding electrons because in this case we assume that they are shared equally. So in a bond, then what we're saying is that one electron belongs to one atom, the other electron belongs to the other atom, which is why we take 1/2. So now, how do we optimize them? Well, the way we optimize them is like this. What we say is that small or zero formal charges on individual atoms are better than larger ones. So if we calculate a formal charge, we try to stay as close to 0 as we can. So we'll have integer values like 0 or -1 or +1 or -2, +2, and so on. We want to get them as close to 0 as possible. But at some point, and this is particularly the case if we have a polyatomic ion, sometimes we cannot avoid formal charges. That is, they have to have a formal charge of something. And if we can't avoid them, what we do try to do then is say that the most electronegative atom should be assigned a negative formal charge. So we come back to our table of electronegativities, and if we're looking at something like a sulfate ion, a sulfate ion is going to have both sulfur and oxygen. And if an atom is going to have a negative formal charge, we want to make sure that that negative formal charge, if possible, is assigned to the oxygen rather than the sulfur. That's what the rule is telling us. So we come back here and let's calculate this formal charge. So have the page out here where you're looking at the formula, and we're going to now calculate the formal charge on each atom. Let's first calculate the formal charge on the sulfur. If we want to calculate the formal charge on the sulfur, we'll just put the S down here, and this is the sulfur now with 4 bonds. When we have a sulfur that has 4 bonds, what we're going to do now to calculate this, following through our formula, is we're going to take the valence electrons on a free atom. So a free atom of sulfur has how many valence electrons? 6. And then we're going to subtract from it the number of lone pair electrons. How many lone pairs are we showing on the sulfur here? 0. So it's going to be 6 minus 0. And then we're going to subtract from this 1/2 of the bonding electrons. Well, this sulfur has how many bonding electrons that are attached to it? 8. 1/2 of 8 is 4. So it'll be 6 minus 0 minus 4, which means we're going to wind up with a formal charge of +2. We are going to show the signs on here, by the way. +2. And then we're going to look at an oxygen with a single bond. Oxygen that has 1 bond. So if we look at an oxygen with 1 bond, we now calculate it. And if we have an oxygen that has 1 bond, we follow the formula. The formula says we're going to take the number of valence electrons on a free atom, which is 6. Then we're going to subtract from it the number of lone pairs, the number of lone pair electrons here, which is 6. There's 3 pairs, and we're counting individual electrons here, so we're going to take 6 minus 6. Then we're going to subtract 1/2 of the bonding pair electrons. So this one here has 2 bonding electrons. 1/2 of that is going to be 1. So we take 6 minus 1, which is going to give us -1. So these are the values. And very often then what we do is we go in and we write those formal charges in here if we want to show them. And if you're going to write it, please put it in pencil because you're going to be erasing these here. So -1, -1, -1, -1, and then the sulfur here is +2. Now if I zoom in on this here a little bit so you can see this, looking something like this right here. Now when we look at this, if you sum together all of these formal charges, what should the sum of all of these formal charges give you? Right, it should give you, and does it give us discharge? Yeah, and that's a good thing. That's a good thing. We want to get as close to this thing as possible. Now the problem with this structure is how many of these atoms have a formal charge equal to 0? None of them do. Okay, so that's telling us that we've not optimized the structure. There's actually a better way to write this structure. And a better way would be one in which we have some formal charges now that get closer to 0. Well, remember, sulfur now lies over here in the periodic table. In other words, lies right here on the periodic table. And if you remember, sulfur is one of those elements that can exceed the octet. So because it's capable of exceeding the octet, what that means is that we could probably take one of these pairs of electrons and move it in here to the center as a double bond. When you put it in here to the center as a double bond now, let's see what happens in terms of the formal charges. So putting it in here as a formal charge now, we have an oxygen that has 2 bonds. If an oxygen has 2 bonds, like we're showing, we then calculate that formal charge. This oxygen is going to start with how many valence electrons on a free atom? 6. How many lone pair electrons are there altogether? There's 4 in here. And how many bonding electrons does this oxygen have? 4. And 1/2 of 4 is going to be 2. So we subtract 2 from here. We take 6 minus 4 minus 2. We are going to get a value of 0. And so now we've taken the formal charge of this oxygen and we've reduced it from a value of, or not reduced it, we actually increased it from a value of -1 to 0. We'd say we reduced its magnitude, and if possible, we want to reduce that magnitude. So we've taken its formal charge and made it become 0. Now, of course, the sulfur no longer has 4 bonds around it. It now has 5 bonds around it. So if we have a sulfur that has 5 bonds, we then calculate the formal charge of a sulfur that has 5 bonds. If we have a sulfur now that has 5 bonds on it, and see what happens, we then calculate it by taking the number of valence electrons on a free atom, which is 6. We are going to subtract from it the number of lone pairs of electrons, which, how many lone pairs are there? 0. And how many bonding pairs are there altogether? 10. There's 10 bonding pair electrons altogether. 1/2 of 10 is 5, and this now becomes +1. So now we've actually reduced the +2 down to a +1. This is better than it was before because these values are now closer to 0. Can we make this even better? And how can we make it even better? Double bond another oxygen, exactly. So if we double bond another oxygen, we get rid of this here. Of course, the formal charge in this case changes from a -1 to 0 because we saw that when we double bond an oxygen that the formal charge is 0. Now we have sulfur. This sulfur has 6 bonds. So now the sulfur with 6 bonds, if we were to calculate its formal charge, we start with the number of valence electrons on the free atom, which is 6. We subtract from it the number of lone pairs, which is 0. And how many bonding pair electrons does this sulfur now have? 12. 1/2 of 12 is 6. 6 minus 0 minus 6 gives us 0. And we then get rid of this here now. We say that the value of the sulfur is 0. And we've now reduced these all down to a value of 0. We still have some negative charges, negative formal charges. We can't avoid it because in this case the sum of the formal charges has to sum to be the charge on the ion. So if we do have something that has a non-zero formal charge, which element should it be assigned to? It should be assigned to the one that has the
Greater electronegativity.
greater electronegativity. And does oxygen have the greater electronegativity in this case?
Yes.
It does. We come back here, we see that the electronegativity of oxygen is 3.5 versus the sulfur here, which is 2.5. And that means that in terms of optimizing the structures, we have now optimized the structure of the sulfate ion. Now, you maybe notice something else we've done here. What else might this one also have?
Greater bond energy.
Well, bond energies. What did we just look at?
Oh, delocalized.
Delocalized electrons. And why might this one have delocalized electrons? Because we don't know whether which of these oxygen atoms that we would have chosen. Why didn't we choose these over here? If you find yourself in a position where you have to choose, then resonance is often likely to occur. So this one may have resonance. I don't know whether it does for sure, but very often if you find yourself having to choose, resonance is possible and you will have delocalized electrons present. And whether that is the case for sulfate or not, I honestly don't know, but it is likely that this would also then have resonance. Okay, anybody else? Okay, here's another way we can calculate. We just calculated using a formula. Here's another way that you can calculate formal charges. And this is a way to do it graphically. And I'll put these now in blue. So what I'm going to do now is go back to our definition of formal charge. And in our definition of formal charge, it says that we're assuming that bonding electrons are shared equally and that the lone pairs belong entirely to one atom. So if they belong equally, what we can do here is basically just think of dividing these up like this. And if we divide them up, remember that each line represents 2 electrons. So you can think of there being 1 dot on each side. And so now if we're thinking of it graphically, then we can just do this math in our heads. Because an oxygen starts with how many valence electrons?
6.
6. And now we're showing it with 7. So 6 minus 7 is?
-1.
-1. And that's it. You look at this oxygen. If we're dividing it up, remember there's still 2 dots in here. We start before it bonded. It has how many valence electrons? 6. And now we're showing it with 6. 6 minus 6 is 0. That'll give us this value. Sulfur starts with how many valence electrons? 6. And now once we divide it up, each one is being assigned 6. 6 minus 6 is 0. So if you want to do it graphically, this is a way to do it graphically without looking at the formula, as long as you remember the definition of what formal charge is, that the bonding electrons are shared equally between the 2 atoms that are involved. Again, also remember that this is a hypothetical charge. It's not a real charge. It's not that the sulfur is more positive or more negative or anything. It's just a way for us to help determine or decide which structure is the best structure. So when you're done, of course, we don't leave these in here. This was just something that I added in to help us think about it when we calculate those formal charges. All right, let's now do this for the sulfur trioxide. Draw the best structure for sulfur trioxide and draw the best structure for the chlorate ion. And when I say draw the best one, draw the one that optimizes the formal charge on each atom. So draw the best structure, the one that optimizes the charge, optimizes the formal charge on each atom. And actually, why don't you do sulfur trioxide? We'll do the chlorate ion altogether. You can give the chlorate ion a stab.
Because here it says that sulfur is an exception to the octet rule, it forms more than a complete octet.
Yes.
What if I make 2 double bonds? It'll be like, if I just make 1 double bond, it'll still fulfill the temp, it won't be more than the octet.
Yeah, if you make 1 double bond, then you will have one octet.
I thought how much more than the octets.
You can have more than an octet on the sulfur, yes. So, you want to reduce them. If you can make more than an octet, then you should make more than an octet. Yes, sir. Well, formal charges, they like to play the game on you, and the game is, we already talked about charges always show the sign at the back end, but when it's a formal charge, it's not a real charge on the particle or ion, so we put the sign in front. Okay. That's because it's not a real charge. How is our sulfur trioxide looking? Is this going to be the right structure at the end? What else do we need to do to this now? Yeah. So if you know this fact right here, a double bonded oxygen is going to have a formal charge of 0. You're going to make a lot of progress on formal charges very fast. In fact, what can we do to get this down to 0 for every atom? Double bond them all, exactly. We double bond them all, something like this, and then go ahead and calculate the formal charges. Remember, we divide them up like this. We already verified that an oxygen that has a double bond is going to have a formal charge of 0, but we can do the same thing for sulfur here. Actually, we're showing 6 bonds. We already calculated that one up above as well. So when we have a sulfur with 6 bonds, its formal charge is going to be 0. So this would be the way that we'd optimize it for the sulfur trioxide. Okay, any questions on this one? Okay, if we went to the chlorate ion, and the chlorate ion and wrote out its structure, we first of all calculate the valence electrons. We have 7 on the chlorine, 6 on each oxygen, and we add in 1 more. Altogether we're going to have 26. We then start drawing out the structure for the chlorine. We surround it by the oxygens. And now I already know something looking ahead, what it's going to look like, which is why I'm drawing it like this. Remember, you're not in a position where you know what shape yet. I am. We learned about shapes in chapter 10. So it's not minus 18, it's minus 6, which gives me 18 left to go. Is it 20? Of course it is. Boy, am I ever ready for summer. So we come back and we put in 2, 4, 6, 8, 10, 12, 14, 16, 18. We used up 18 here. Where did the remaining 2 go? On the chlorine. You put them in right here. Of course, now we're still missing a couple things. One of them is brackets and the charge. What's wrong with this, though, is that chlorine, now at this point, has a formal charge that isn't very good, I'm sure. So if we calculated it looking at it like this, remember we split these up, what would the formal charge on this chlorine atom be?
5.
When we start with the number of valence electrons on the free atom of chlorine, which is 7. And how many are we showing assigned to it right now? 5. 7 minus 5 is 2. Okay, so the formal charge on this chlorine is going to be a plus 2 at this point, and that's not good. So we want to get it reduced. How do we reduce this down? Start double bonding. So as long as you remember the fact about oxygens, when you double bond an oxygen, its formal charge is 0. You put yourself in good shape. So we put in a double bond here and here. Then the question is, do we put in a 3rd triple bond right here? Well, let's see. Let's say we put in 3 triple bonds. If we put in 3 triple bonds, we divide these up. The formal charge on this chlorine at this point would be, neutral atom of chlorine is how much? 7. How many are we assigning to this chlorine right now? 8. We put in 1, 2, 3, 4, 5, 6, 7, 8. 7 minus 8 is -1. Well, if we come back to our rules for formal charges, we say that if we had to select between them, when formal charges can't be avoided, the most electronegative atom should be assigned a negative formal charge. If you compare the electronegativity of oxygen to chlorine, which one is larger? Oxygen. So if there's going to be a negative formal charge, that negative formal charge should be assigned to which element? Oxygen. So is this a correct structure? No. How could we make it correct? Just put in 1 single bond here to the oxygen. If we have a single bond into the oxygen now, and divide this up, and then calculate it, we've done a single bonded oxygen before. If you go back up here where we did it, a single bonded oxygen has a formal charge of -1. Each of these oxygens here are 0. And if we calculate the formal charge on this chlorine now, we take the number of electrons in the free atom, which is 7. We subtract the number of electrons that are assigned to this one now, which is 7. We have 1, 2, 3, 4, 5, 6, 7. 7 minus 7 is 0. Now the negative formal charge is on the oxygen, and that makes this one preferred over the other one, in which the formal charge, the negative one, was assigned to the chlorine. So this one then, we are in the ability to choose. We choose this one. Says, I choose you. Who says that? The Pokemon dude. I don't remember it. All right. What's his name? Ash? All right. Okay. Any questions on this one? My boys watched that all the time when they were little. And what happened to the Pokemon Go game? That just kind of disappeared, didn't it?
The developer stopped supporting it.
Oh, okay. Okay. Then the last thing we're going to look at is going to be bond energy. Bond energy we are not going to calculate in here. That is, we're not going to calculate actual values, but you should know qualitatively what bond energies represent. So, back when we talked about enthalpies, we said that the average enthalpy change for breaking a bond in a molecule in the gaseous phase is called the bond energy. Now, this part should make sense. Energy is required to break bonds. So in other words, if we have to put energy into something, that means we're absorbing energy from the surrounding. That process is endothermic. And energy is released when bonds are reformed, which means it is exothermic. So the two should be just the opposite. As we already mentioned, as the bond order increases, so does the bond energy. Why should this have a greater bond energy than this one here? There's more bonds holding it together, so this is going to have a higher bond energy than the other one. And then what we say is that the enthalpy of reaction, the delta H, is approximately equal to the sum of the bond energies for the bonds broken minus the sum of the bond energies for the bonds that are formed. Yes?
So if the bonds that are formed are exothermic and the bonds that are broken are endothermic right there, and if you said an exothermic is normally negative, wouldn't the enthalpy change always be positive, since subtracting a negative is always going to be like adding?
Well, what it is, when you break bonds and reform bonds, you're going to wind up with different substances. So when you look at it, and I'm not sure this is answering what you asked per se, but basically what you look at is if more energy goes into breaking the bonds than is given off when bonds are reformed, then the process is going to be one that is endothermic. And if there's more energy that is released when bonds are reformed than is absorbed to them when bonds are broken, then the process is going to be one that is exothermic.
I'm asking about whether it's positive or negative, because in other enthalpy equations they could be negative enthalpies, but in this one we're subtracting the exothermic energy, so exothermic energy is always negative. So
exothermic is always negative, yes.
So does that mean the enthalpy change is always going to be positive for this right here?
For this, no, it will not always be positive. On these right here, let's see, if they form, they're all going to have bond energies which are, trying to think now, it's exothermic. So when bonds are formed, it's exothermic. Yes, they should be. Always, you said exothermic. Negative values, right?
Yeah, we're subtracting the negative.
Yep.
So
So if you're subtracting a negative, I'm trying to think right now how that works. Do you have a point to make?
No, I have a separate question.
Okay. I'm still trying to think on yours. I'll have to get back to you on yours. You are right, though, I'm pretty sure. Go ahead.
I just have a question regarding carbon. Since it can bond to itself, is it possible to get a four-way bond going on, or is it just the most it can do is three?
There is such thing as you can have a quadruple bond. Carbon, to my knowledge, doesn't do it. Some of the transition elements do. We have, and this is a chapter 10 topic, we'll only be learning about sigma and pi bonds in chapter 10. A sigma bond is a single bond between two atoms. It's the first bond that forms. And then pi bonds are going to be the second and third bonds that form between two atoms. We'll talk about how that affects things like rotation between atoms. But yes, there is such a thing as a fourth bond, and that's called a delta bond, which your book doesn't even get into.
Okay.
Yeah. Okay, anybody else have questions?
Do you have the list of what polyatomic?
I don't have that, but I should get that out. I think I did actually post it into your D2L. It's kind of hidden in there. If I were to look in your D2L, let's see here. And of course, I'm logged out right now. But I'm pretty sure it's in there earlier. If somebody sends me another email reminder today, I know I have another one of yours that I need to respond to. I'm hoping I have enough time today to get those things in there.
So those are what we want to know on the next exam.
I don't think, I'm trying intentionally to avoid assigning them, but for the final exam, yes.
Okay.
Yeah. So, but there are ones like we did already here, like today, carbonate, sulfate. If you know your carbonate, your sulfate, your phosphate and such, you'll be good. We won't be doing too many things like a hypochlorite or things of that nature. Okay. Right, so test is going to be on Tuesday. Your test is going to be over chapter 6, 7, 8, and 9. So chapter 7, 8, and 9. You have your list of problems that you should be practicing. That is the study guide. I did pass out a syllabus supplement which says what you should be studying right now. And that syllabus supplement will give you an idea of your expectations of what you need to know for the exam. And it's no different than the things you've been doing here in class. I think maybe in chapter 7 there's some of your actually calculating energies, different energy levels and such. But if you're doing that on the exam, you're going to be provided those formulas. So the combination of being here in class and seeing what we've done for examples and doing these here, there shouldn't be any surprises whatsoever come your exam time. What I would like to do here today to wrap up the hour, and as far as things like formulas, don't memorize formulas. Any formulas that shows up as a key equation in the back of the chapter is something you'll be provided with. If it doesn't show up as a key relationship or key formula in there, it's not going to be provided. So these things like drawing out your Lewis diagrams, you are not going to get this thing to use on the exam. So you need to be able to know which elements are exceptions to the octet rule, which ones conform to the octet rule. You should be able to write out resonance structures. You should be able to calculate formal charges. Those are things that you do on your own to come up with those structures. So about the only thing I just lied about was the formula for formal charges. I would provide that for you. But other than that, this is not something that you get provided on an exam. You do need to know how to write out those structures. So that said, today we have a few minutes left here. This will allow you to practice on some of the things that we've gone through thus far. If you only have limited time to practice and can't get through them all, the ones that I would practice for sure, on the first one, this is 39C in your, or number 39 in your book. So I'd practice letter C on the first one. The next one is number 51 in the end of chapter 9. I'd practice letter B if you're going to practice one. The next one is number 63 in your text. If you were to practice one, I'd do letter A. And the last one is number 65. So if you only have time to practice one of each, before you leave today, to make sure you can do them, I'd pick out letter C on the first one, B on the second one, A on the third one, and then make sure you can do the very last one. That's here. So that's it for lecturing today. We have about 15 minutes here to work. Help each other out. I will walk around and help you out.